All right then, so let's continue the calculation of energy transport by the Hadley cell. We already wrote an expression for it. We can just look at the contribution from each term, remembering that the temperature gradient in the upper atmosphere gets flattened out pretty much by the heat transport itself, and we'll see that the vertical profile of the moist potential temperature gets flattened out as well because of the convection. Okay, then what terms are doing the work? So remembering our expression of the dry static energy, meridional transport is obviously multiplied by V. We are just looking the net transport by the Hadley cell in the meridional, still not accounting for any longitudinal variations in the flow. The vertical gradient of dry static energy is ddz of the Cpt plus gz, which you can expand into Cp dt dz plus g, and I think you know where we are going. So Cp dt dz plus g over Cp, okay, take the Cp on the other side. This is greater than 0 in the low latitudes, right? You have dt dz, which is negative, and g over Cp, which is positive. The sum of that tends to be positive. And what does that mean? So you add, essentially that means just the dry static energy transport is basically not very large at all. In fact, it is slightly towards the low latitude from the high latitudes because of exactly what we said before. This gradient is small and the air is actually converging from cooler temps to the warmer temps. So if you look at the Hadley cell, you actually are moving very little heat out towards the extratropics beyond the Hadley cell. You actually have to add the moisture term LQ to get the net transport to be positive at all. It is still very small, as we will see, but here is the humidity distribution, this zonally averaged meridional section of specific humidity Q that we had seen before. You remember we saw this and the relative humidity. So the humidity levels near the surface are high because the evaporation tends to load the boundary layer, and then as you go up in the atmosphere the humidities drop off, because even during the convection, remember that humidity moisture tends to rain out, and then you have dry air coming down, etc. And as you go to higher latitudes, temperatures cool off, and our Clausius-Clapeyron is going to give us much drier humidities. Okay, so rho v over rho is the specific humidity. So zonal average moist potential temperature is fairly uniform in the vertical because of convection itself. Okay, so flat gradient up here and flat vertical gradient up here, down here in the low latitudes. So the Hadley cell basically transports moist static energy poleward, but the net energy flux is very weak if we integrate that equation. Kinetic energy terms are very small. Just remember that as well. Okay. So tropical moist static energy has a weak vertical gradient, so annually averaged energy flux by the Hadley cell is poleward, but it's very weak. So who's doing all the work then? We'll see soon that it's actually the ocean that's doing most of the work in low latitudes. Okay, I got a little frog in my throat, excuse me. Incredibly humid here in Mumbai. So let's look at the schematic of the energy transport and the angular momentum transport. So the tropics have a net radiative gain, and the Hadley cell is lifting it from the surface to the upper atmosphere and trying to transport it towards the poles. So it sinks in the subtropics, and we have already said that the cells to the north of the Hadley cell are fairly weak, and the energy transport has to be done by the eddies. So as far as energy transport is concerned, we have to take energy from warmer temperatures to colder temperatures, and there is a net radiative loss here and a net radiative gain here, as opposed to the angular momentum, where there is a net angular momentum gain in the easterlies domain of the low latitudes. The Hadley cell is also transporting angular momentum, and then eddies are transporting the angular momentum northward as well. But the mid-latitude westerlies obviously are losing the momentum to the surface. Here the energy loss is to space, whereas momentum loss is to the surface, because westerlies going in the same direction as Earth are being slowed down by the friction, right? In the tropics, in the trade wind region, easterlies are being slowed down, means they are gaining angular momentum, westerly angular momentum, whereas in high latitudes, westerlies are losing their momentum to the ground. That's the main story. Hadley cell is part of the energy transport, but it's got a very weak net northward transport, and most of it is accomplished by the moist dynamics, convection lifting the energy and transporting it poleward towards the subtropics. Okay, that's the simple story.